Hello. Hi, everyone. Ah, I want to first double check if there's an echo. There might be an echo. So I'll see if there's yep, I think that has been fixed. So next thing I'm going to ask is, can people hear me? If you can hear me, give a wave. Actually, I've got co-hosts who I can see. Just wave if you can hear me, because then I'll know that at least it's going through in ours. Melody and Corey, if you can hear this, can you wave? At least, yes, good,
Oh,
good, good.
oh,
Okay.
there you go.
Yeah, this works. Okay, great. So let me introduce. So first of all, welcome to our YouTube channel. If you've been here recently, you know that we have these live solves that we run, which have some extraordinary people who are high school students who are experts at math contest problem solving. And then we try to make this whole thing fun. Well, today we're very happy to be collaborating together with Math League. Math League is they're interesting. They run a series of monthly contests, and I quite like them because there are then these monthly opportunities to work on math. I should probably say who I am. I'm Po-Shen Loh. I'm actually calling you in right now from Carnegie Mellon University. I'm giving you a tour of our beautiful math building, which is a rectangle with rectangles inside it. But in any case, it's nice to meet all of you guys. And today we are going to do some questions from the recent round, the qualifying round. There's a middle school math competition in the Math League. And if you haven't joined Math League, I do recommend you do, because this is a chance to do mathematics in a fun contest type environment every single month. If you're new to this, go to mathleague.org. That's the org. There's also a mathleague.com. That's different. But the mathleague.org, if you go in every single month, you can do this kind of contest. And we'll always have this end of the month get together where we solve the problems. Where we means not me, because actually, I unfortunately am usually on the road. In fact, I just got in today from, I was speaking at Harvard earlier, and tomorrow I need to be in Westchester, Pennsylvania. However, we're lucky to have two extraordinary people. So there's a live program which we run where we find high school students who are really kind and also really, really clever. And they have the equipment to make the live stream look better than I could ever do. With that, I'm going to say today we have Melody and Corey, and they're going to introduce each other, and then they'll take it from here. See you guys.
Hey, hi everyone. I'm Melody, and today I'm here with Corey, who's a senior at Lexington High School. And he's been involved in math competitions since he was in middle school. And besides math, he enjoys playing video games, spending time with his friends, as well as playing sports and being outdoors.
Hi guys, I'm Corey. So I'm here with Melody, and Melody is a high schooler in Oklahoma. She's a former Math Counts national competitor, a two-time Amy qualifier, and has taught math for 2 years. Outside of math, Melody has played violin in many state orchestras, including the Oklahoma All-State Orchestra and Oklahoma Summer Arts Institute Orchestra. In her free time, she enjoys playing Tether.io and making ramen. So hello to Melody. Great. Now, today we're going to be working through the Math League problem. So let's start with problem one here. So problem one is already kind of fun and interesting. It's very short. It says, how many more interior diagonals does a regular octagon have than a regular hexagon? So let's see. How many more interior diagonals? So we're looking at the diagonals here, and we're looking at an octagon and a hexagon. So let's first draw our octagon here. Octagon is eight-sided. So let's look at this. And we want to draw all of its interior diagonals. So bam, 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 bam. There's a lot of them. I'm not going to draw all of them. Let's try and draw our hexagon here. So our hexagon has 6 sides, and it also has interior diagonals. It's actually much easier to draw the interior diagonals here, but let's do this in a way where we don't have to draw it out. Is there a way to do this without drawing it out? Well, let's take a look like this. This is a question about combinatorics, but there's a simple way to explain this and a more complicated way. So let's do this the easier way first. Let's see, how many diagonals does this regular octagon have on the left? Well, let's make a new slide. An octagon has 8 sides. So if I consider this one red point right around here, if I look at this red point, how many diagonals does it have? Well, I can draw all of these, right? Like that. All of these here. There's 7 additional points that I can draw to. So this singular point right here can give us 7 more lines. Oh, the text on the screen is fuzzy. Oh, Hopefully the images aren't too fuzzy. So here, this one point gives me 7 red lines. And what I can do is I can do this for all the other points too. And I draw a bunch of lines. And there's 8 total points. So what I'll have is 7 times 8 red lines. But the key to combinatorics here is there's actually a divide by 2 here. Now, the reason why we have to divide by 2 is because when I draw this first red line up here, you can notice that, well, I can start from this corner and draw this line left, but I can start from this other corner and draw the line right. So what happens is we overcount it twice. So we'll end up with 7 times 8 divided by 2, which is 28. And that's going to trace out all of the different lengths from any point to any other point. But because we want to count the interior diagonals, we actually have to subtract 8. So if you look on the outside, let's see, let's use yellow. On the outside, we have 8 yellow edges here that we don't want because they're not interiors. If we go back to the question, it asks specifically for interior diagonals. I know it's a little fuzzy, but hopefully you guys can see that if I subtract 8, then I get 20. Now, let's just do this again for the hexagon. So the hexagon has 6 sides. Actually, let's just count. I think the hexagon is easy enough to count. So the hexagon should have, I can just draw this like that. 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So the hexagon will have 9 interior diagonals. So the hexagon has 9, the octagon has 20. The difference is, can somebody tell me what the difference is? $11, great. So Simran says 11, exactly. So it's just 20 minus 9, which should be 11. And that gives us the first answer of 11. And great. So Melody, do you want to look at question 2? And I'll make it a little bigger so you guys don't think it's too fuzzy.
Oh, yes. And today we're only doing the odd problem. So this is question 3. So we'll try to get through most of these. But this problem reads, the letters in the word banana are arranged at random. What's the probability that the first and last letters are the same? Oh, so the first thing I notice is that if we start with banana, it's impossible for the first and last letters to be the same because there's only one beat. But let's just say, let's split this up into cases, actually. So let's say the first letter is an A, so then the last letter is also an A. So we have an A here, and then we don't really care about these, and also an A here. So let's just calculate the probability that the word looks kind of like this. So the probability that the first letter is an A, well, there are 3 A's and there are 6 total letters, so that would be 3/6. And then the last letter is an A. Now that we already used an A, there's 2 A's left and 5 total letters left, so 2/5. So I think this is our first case. I'll make another slide for the next one. So we have banana, just so we don't forget. I think our only other possibility is if the first and last letters are N's. So we have N, and we don't care about these, and also an N. So there's 2 N's and a total of 6 letters. So the probability the first letter is an N is 2/6. And then we have an N at the end. We have 1 N left and 5 letters left. I kind of forgot what we just wrote down. Oh, this part is 3/6 times 2/5. So 3/6 times 2/5. We just have to add our cases together now. Okay, so if we just make this work out, 6/30 plus 2/30 equals 8/30. So I think the probability should be 4/15. Yes, 4/15 that the first and last letters are the same.
Great, great. So that was really fast. That was question 3. Now, I think question 5 will also be a pretty fast one. So question 5 says that Kirby has 5 red dice, 6 orange dice, 7 yellow dice, and some green dice. So these are some key information to keep in mind. But when he chooses a die at random, the probability of him picking a red or yellow die is 3/2 the probability of him picking a red or green die. How many green dice does Kirby have? Great. So let's make a new slide for this. And what do we want to write down? Well, first of all, the question gives us red dice, orange dice, yellow dice, and green dice. And the question says that, oh, there's five red ones, 6 orange ones, 7 yellow ones, and we don't know how many green ones. So 5 red, 6 orange, 7 yellow, and we don't know how many green ones there are. So let's just call this X. So what we have is now the next part of the question tells us that the probability of him picking a red or yellow die, the keyword is going to be right here, red or yellow, is 3/2 the probability of him picking a red or green. So let's see. What is the probability of picking a red or a yellow dice? Well, in total, there are 5 plus 6 plus 7 plus X dice. That's how many total dice that we have that we can choose from. But we want to pick only the red and the yellow ones. So that's 5 plus 7 dice. So out of all the total dice, we only want to pick the red and the yellow ones, which is 5 plus 7. And now the other part of the question says that it's 3/2 the probability of him picking a red or a green dice. So let me just highlight this in yellow. The red or green dice over here somewhere. Yep. The red or the green dice. So that's going to be red here and green here. So again, we'll have the bottom, which is all the possible die that we can pick from, 5 plus 6 plus 7 plus X. But we only want to pick the red and the green. So this is red and this is green. That's going to be 5 plus X. And what does the question tell us that relates these two probabilities? Well, we know that the first one is 3/2 times the second one. So I can write equals 3/2. Or just more simply, I can replace this thing right here with 3/2 vertically like that. And now we can solve this algebra equation. But it's actually pretty simple because what we can do is we can cancel out the bottom because we can see that on the left and the right, we both have this denominator. So we can just get rid of it. So what we're left with is going to be 5 plus 7 equals 3/2 times 5 plus X. So why don't we just do some algebra here? The left is going to be 12. And the right, let's leave it in place, 3/2 times 5 plus X. Now, what happens if I double both sides? Well, if I double both sides, I'll get 24 on this side is equal to 5 plus X. I can, 5 plus X. And then I can expand this to get 24 equals, actually, let's divide by 3. Dividing by 3 gives us 8 equals 5 plus X. So we should get X equals 3 if we divide by 5. Great, great, great. So it looks like a lot of you guys in chat are also giving out equations, and all of those equations also solve to X equals 3. So if we look at the answer, and the answer is going to be 3. Perfect.
That was a really fun question. And our next one is, what is the least number of chords necessary to divide a circle into exactly 7 non-overlapping regions? I think a good way to do this is to just draw it out. So I apologize for my bad circle, but to get the least number of chords, I think we just need to try to get each chord to split the circle as many times as possible. So for the first one, we don't have much of a choice. And I'll definitely just split the circle into 2. And then same for the second one. Now there are 4 regions. But the third one, let's see if we can get this into 7 already. If we draw it here, that doesn't split it up into that much. There's only 6 regions there, but we're pretty close. I think that if we intersect this chord and this chord, then we can split the circle into 7 regions. So if you draw the chord there, we'll have let me change my color real quick. We'll have this region here, and this is 7. So yeah, you only need 3 lines. It's perfect. Just like the last question, I think. So the answer to this one should be 3. Yes.
Great. Okay, so now let's look at question number 9. So can you guys see this clearly? I have it on as big font as I can. Can I see if you guys think this is clear enough for you guys? I'll also read the question out, so I'm not super worried. But how clear is this for you guys? Clear enough, pretty clear. Great, great, great. I'm glad to hear that. Okay, so let me read this through. Anna is feeling bored, so she decides to choose another number. Okay, choosing a number. This time, she randomly chooses a not necessarily whole number between 0 and 11 inclusive. Anna then draws a circle with that number as its radius, and Bob draws a sphere with that same radius. What is the probability the surface area of Bob's sphere is numerically greater than its volume, and the area of Anne's circle is numerically greater than its perimeter? Express your answer as a common fraction. Okay, so this question is very, very long. Let's try and break it up slowly. So I'm putting it onto a new slide. We don't need this many words onto our scratch paper. What should we move? What should we put? What are the key informations to put? Well, first thing is we know that Anna is choosing a number. So we have this number. What do we do with it? Well, what is this number? Okay, so we know that it's not necessarily a whole number, so it could be a fraction, but we know it's between 0 and 11. So we've got this number, and it could be a fraction, but it's between 0 and 11, somewhere in between 0 and 11. And then what about this number? Okay, Anna draws a circle. Let's call this number, why don't we call this number x? So Anna draws a circle with radius x. And we're asked to find, what do we care about? Well, what is the probability that the surface area of Bob's sphere, okay, let's skip that. And the area, so the area of Anna's circle is numerically greater than its perimeter. So we want this circle to have area, whoops, area is greater than perimeter. I'll just write P. Because we want Anna's circle to be numerically greater than its perimeter. And what do we want? Okay, and what about Bob? So Bob draws a sphere. Let me draw a sphere here, okay? So this is a sphere. This is Bob's sphere. What do we care about the sphere? Well, we want the probability that the surface area of Bob's sphere is numerically greater than its volume. So we want the surface area to be greater than the volume. Great. Okay, so we got circles, spheres, areas, perimeter, surface area, and volume. Let's do these out separately. Why don't we do that? So, great. So let's first do the circle. So if we look at Anna's circle right here, and we have radius x, I want the area to be greater than the perimeter. Guys, tell me, what's the area of a circle if I know its radius? Ooh, okay. Oh my gosh. So I see Elise has all of the formulas, and hopefully you guys also know the formulas. Exactly. And Mira's right. We're trying to compare the formulas. So what's the area formula? It's pi times radius squared, right? And here the radius is x. So I have pi times x squared. And I want this to be greater than the perimeter. But what's the perimeter? Well, it's 2 pi r, right? But here r is x, so it's 2 pi x. So this is the first equation that we want satisfied. Why don't we try and simplify this equation? How do we simplify it? Well, I see that we have a pi on both sides, so I can get rid of that. And I end up with x squared is greater than x. Or if I divide by x, I end up with x is greater than 1. Okay, cool. So if I want the area to be greater than the perimeter, I just need the radius to be at least 1. What about the sphere? So let's make a new slide. What about the sphere? So now let's look at Bob. Bob has a sphere, right? Let's try and draw a sphere here. Bam, 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 bam. This is a sphere that Bob has. Great sphere, guys. And we know that the sphere has radius equals x, right? Radius equals x. Radius equals x. And I'll draw it visually as well. So looks like around here is x. And what do we care about? Well, let's go back. We want the surface area of Bob's sphere to be greater than its volume. So let's go here. We want surface area greater than volume. Now, once again, the surface area of a sphere is, can somebody give me the formula? Does anybody remember the formula? It should be 4 pi r squared, right? And here r again is x, so it's 4 pi x squared. And the volume is 4/3 pi r cubed, which is 4/3 pi x cubed, like that. Nice. Okay, great. So it looks like you guys already know this. So let's first cancel out the pi again. And let's cancel out the 4 too. So I'm left with x squared greater than x cubed over 3, okay? And then what happens? Let's see. Let's divide by x squared. I'll get, let's move this. Let's move that. There we go. Divide by x squared, I get 1 greater than x over 3. So I have 3 is less than x, like that. Okay? And then here, okay, wait, let's go back for a second. So yeah, so here we get, oh, I forgot the 2 on this side. Yeah, you're right. Let's see, let's move this x. Here I forgot a 2. This is supposed to be 2 pi x. So after I cancel out the pi's, it should just be 2x. So x has to be greater than 2. Let me erase that. X should be greater than 2. Good reminder. Somebody in chat said that. I forgot a 2, so I was looking for it. Yeah. So for the area, Anna has to have x greater than 2, but Bob has to have x less than 3. So out of the 0 through 11 that we can choose our numbers from, we're only able to have x between 2 and 3. So that means that we only have this length 1 interval out of this length 11 interval. So the probability should be 1 out of 11. Does that make sense to you guys? Good, good, good. Great. And if we look at the answer key, it should also give us, yep, 1 over 11 right here. Yep. Nice. Came out well. Yeah, great. Now, Melody, can you take us through the next one?
Oh, that question came with a lot of tricks to simplify a question, and I think that might be useful to this one as well. So I'll also read this out loud. In how many ways can a collection of 5 identical red blocks and 7 identical blue blocks, all of which are cubes of the same size, be placed into several 1 by 1 by n towers such that n is greater than equal to 2, and the top and bottom blocks of each tower are red? Okay, this is also a huge problem. I think what I'm getting from this question is that we have some big towers. Oh, sorry, my pen is not working. We have some big towers that look like this. So we have a red block, some amount of we don't know blocks, and then another red block. I'll draw them sideways too, because they're towers. They can be flipped sideways, and it's easier for us to see. So it'll kind of look like this. So we have the height is n, where n is greater than or equal to 2. So the smallest or the shortest tower has to be a 2 by 2 tower. Let's see. If it's a 2 by 2 tower, we'll have 1 block on the bottom that's red and 1 block on the top that's red. And I think that's our only option. So height of 2, let's just call this the 2 tower. If we have a 3 tower, the one on the bottom is red, and the one on the top is red, and the middle one could be red or blue. So I guess there's 2 options for this tower. 2 options. Also, I think this is getting somewhere because the first tower, we have no blocks in between, so there's just 1 tower. The second tower has 2 or has 1 block in between, so you can make 2 towers out of it. I'm sure that the tower with height 4, there are 2 blocks in between. So the first, I'll draw it out just for completion, I guess. So this has to be red, and this has to be red. But this one could be red or blue, and this one could be red or blue. So that's 2 times 2, which is 4 tower options. Yeah, Charlotte's exactly right. Towers of 2. But soon we'll run into a roadblock because the problem tells us we have 5 red blocks and 7 blue blocks. What if the height is like 10? We can't have 10 red blocks in the middle. So now we're kind of stuck. We can go up until, well, since we have 5 red blocks total and we're using 2 of them on the ends, we have 3 red blocks that we can put in the middle. So let's just say for our tower of height 2, we have 1 option. Of height 3, there's 2 options. Of height 4, there's 2 squared options. And of height 5, there's 2 cubed options. Let's draw out a height 6. This can be red. This is red. Yeah, that's 6. Okay. So clearly we can't have 4 red blocks in there because we're not given that many red blocks. So let's see. I think we could split this into cases. So we can have 1, or let's say our first case is 0 red blocks. So it's all blue blocks. And then, or we could have 1 red block in there, or 2 red blocks in there, or 3 red blocks in there. So we can't have 4 red blocks. Oh, I'll read the message. We have 10 left. For the first tower, 10 possibilities. Second tower, 10 times 9. I'm not sure. This problem is kind of tricky. It's really prone to overcounting or undercounting. I'll try to keep going with this strategy. Well, we'll see. So for this all blue tower, there's only 1 because we can't exactly mix those up. But for 1 red and 3 blues, we can like put the red in the 2nd slot, or in the 3rd slot, or in the 4th slot. So we can make 4 towers out of this. And then 6 towers out of this one, and 4 towers out of this one. Yeah, okay. And then for the next one, if we have 5 blocks in between the red, then we can have 5 blues, or a red and 4 blues, or 2 reds and 3 reds. Yes, it looks suspiciously like Pascal's triangle. Yeah, so I'm hoping this means we're getting kind of close. I'm writing all over my face. I'm running out of room. I'm so sorry, guys. I think we're getting close. Is there like, does anyone see a cool pattern in here, or should we just keep going this way just to make sure we're doing it right? Okay, let's just keep going since no one said anything. So if we have 6 blocks in the middle, we can have, I'll make a new slide. We're running out of space. We can have 6 blues, a red and 5 blues, 2 reds and 4 blues, or 3 reds and 3 blues. Yeah, Pascal's triangle because n choose k results in the numbers in the triangle. Yeah, Pascal's triangle is like secretly in every counting problem somehow. So knowing your triangle well will definitely help you a lot. So I believe this is 1, 6. thought I wrote this down somewhere, but I might have lost it. 15 and then 20. And then, oh, the YouTube's, I'm sorry. Oh, yeah, Corey. Do you see a better way to do this problem? Because this
Yeah,
one.
yeah. Wait, it's just a continuation of what Melody was doing. So Melody was showing us some really, really cool stuff with Pascal's triangle. And that's what I want to add on to. But before we go on to Pascal's triangle, why don't we try and understand this question one more time? Because this is a very confusing question. So yeah, so Rohan's saying that the order doesn't matter. That's true. There's a lot of aspects to this question. But what it's saying is that we have 5 red blocks and 7 blue blocks. And let's just say they're all one by one by one. And I want to place them into towers. But the question says I can place them into several towers, such that the top and bottom blocks of each tower are red. So let's say I have this tower right here, and you can imagine just dropping cubes into it, right? Now, if I have just one tower, guys, if I have just one tower, then all of my 5 reds and all of my 7 blues will go into the same tower. But I know that this tower has to start with red and it has to end with red. But the remaining, what is it? So I have 5 red, and I have, whoops, let me just, it's fine. And then I have, let's see, 7 blue, right? I won't use blue here. I'll just use 7 blue. 5 red ones and 7 blue ones. If I put them into one tower, we're going to be using what Melody was talking about, which is, okay, in the middle, well, okay, 5 reds, 7 blues, but the top has to be red and the bottom has to be red. So in the middle, what we're left with is 3 reds and 7 blues. Is that all okay for everybody? 5 reds, 7 blues. One's on the top, one's on the bottom. So there's 3 reds left and there's 7 blues left that I have to put into the middle because there's only one tower. Yeah, great. So now this is what Melody was talking about. I have 3 reds and I have 7 blues that I want to put. So what I like to see is exactly what Melody is. So I can have R, B, 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 bunch of Bs, or I can have like R, B, B, R, R, B, 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 whatever. And what this is it's sort of idea of Pascal's triangle. Because we're a little bit short on time here, I'll show you a trick. This is what I like to call the Hong Kong trick. I learned this, oh my gosh, this was the first math trick I ever learned. It was incredible. So what happens is, ooh, how should I explain this? Okay, this might be a little tricky for you guys, but I hope you guys can deal with it. Hopefully you guys can try and follow along. And if you guys get anything out of this, that'd be great. And I know some of you guys are definitely really clever, so you'll understand all of it. But if I have a red marble, an orange marble, a yellow marble, a red marble, and a white marble, and I want to just order them, then I'll have 4 factorial ways, right? This is what factorial means, because I can choose the first color to be the first one, the second color to be the second one. I have 3 colors left. Then I'll have 2 colors left for the third one, and finally 1 color left for the last marble. So it's 4 factorial. Now, if I want to do this in this case, where I have red marble, red marble, red marble, blue marble, blue marble, blue marble, blue marble, I'll have 10 factorial ways, right? But I'm missing something. What I'm missing is that if I have a bunch of yellow marbles, then orange marbles, then orange, 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 yellow, red, white is no different from orange, 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 yellow, red, white, because the colors are all that matters. So here, these 3 reds and these 7 blues, they're the same. They're clones of each other. So we have to divide by how many clones of each other there are. And I'll just put this on the board for now, but it's going to be divide by 7 factorial, divide by 3 factorial. Because in any sort of listing, like R, B, 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 there's going to be 3 factorial ways to just sort the red marbles. Because I'll have red 1, red 2, red 3, red 1, red 3, red 2, red 3, red 1, red 2, red 3, red 2, red 1, red 2, red 1, red 3, red 2, red 3, red 1. That's 6 ways. That's 3 factorial ways that the red marbles can mix with each other. But the red marbles are all the same. So I have to divide by that many times. I'm overcounting. And the same for the blue marbles. And the red marbles will be 3 factorial, and the blue marbles will be 7 factorial. So I'll end up with this. This is from Pascal's triangle. but I'll have 10 times 9. Okay, let's do this on a, let's just move to the side. I'll have 10 times 9 times 8 times 7 times 6 times dot 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 divided by 3 times 2 times 1 times 7 times 6 times dot 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 dot, right? And then what I can do is this part and that part, well, they're the same, so I can cancel them out. So I'm left with 10 times 9 times 8 divided by 3 times 2 times 1. And that's going to give me, well, I'll cancel out the 3 to get a 3, cancel out the 2 to get a 4, and that's going to be 120. Oh my gosh, is the answer 120? Let's take a peek. Oh, the answer is not 120. The answer is 156. So we're missing something. That's why with the go back to our question, remember, the question says we can have several towers, not just one tower. So we have 120 ways to just build one tower. But we could also build 2 towers, right? What if we had 2 towers? One tower here, bam, one tower here, and then another tower right here. Okay, we do not know how tall these towers are, but we know there's 2 of them. Let's say there's only 2 towers. Again, the question says the top has to be red, the bottom has to be red, the top has to be red, and the bottom has to be red. So we have 5 reds, and we have 7 blues. But look, bam, 1, 2, 3, 4. 4 of the red ones are gone. So I only have 1 red one left and 7 blue ones left. Okay? And I want to put these into our towers. So first, some tower can have no blocks in the middle, right? I can just have a red block and then a red block, and that's fine. So I don't need to put these 8 marbles into 2 towers. Like I could put 0 marbles in one and the other 8 in the other. So let's take a look at that. Oops, let me change colors. 1 red marble, 7 blue marbles that I want to put into 2 towers, but I could put 0 and 8, 1 and 7, or blah, 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 right? So let's start with the largest case. Let's say all of these marbles are in the same tower, okay? So then we'll have 1 red and 7 blue in the same tower. But, how many ways are there to do that? Well, I could have red and then 7 blues. Okay, wait, how about I do it this way? I have 7 blues, right? Blue, 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 blue. Oh God, that's a big blue. Blue. There's 7 of these, but I can put a red marble here, or 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 here. So I can put it at the very front, or at the very end, or anywhere in the middle. In total, there's going to be 8 of these spots. So this case, I'll write down an 8. Okay. So what if we kick out one of the blue marbles? What if we put one of the blue marbles? So right now we have 2 stacks, right? We have one stack here and 1 stack here. 1 stack here and 1 stack here. So let's just assume that the 1 red marble is in the stack on the left, because there's no difference between 2 stacks, right? Like if I gave you a starburst here and a starburst here, like you could switch them around and it doesn't matter. So let's just assume the red marbles in this stack. And if all of the 7 blues are in this same stack, there's 8 ways. But what if there's only 6 blues? So there's 8 ways, right? But what if there's only 6 blues? Then I'll write blue, 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 blue again. And again, I'll have red here, red here, red here, red here, red here, red here, or red here. And that's 7 ways. So if I have 5 blues, then I'll have 6 ways. If I have 4 blues, I'll have 5 ways. If I have 3 blues, I'll have 4, 3, 2. And this final one is when I have no blues. So I just have red, and then all 7 blues are here. That's 1 way. So now I'm going to have to take all of this stuff, 8, 7, 6, 5, 4, 3, 2, 1, and add all of them up. And what do I do? Well, there's a formula for that, right? Or you can just add them up, and you'll get 36. So if we take these 36 and we add them to our previous 120, what we're going to get is our correct answer of 156. How does that feel? Great, great, great. All right. And guys, okay, listen. This is very, very complex for like middle school math or like anything like Ooh, this is a pretty hard question. There's a lot of stuff in there, especially with the Pascal's triangle. Melody was trying to build up to this idea of the Pascal's triangle. I kind of skipped it a little bit. I built off of what Melody was talking about, and it was extending what she was talking about, but it's a little advanced for us here. So let's just, so the big step was the 10 factorial divided by 3 factorial, 7 factorial. But let's just hope that if you guys get the gist of it, that's good. I still am confused anyhow. Okay, well, this is called, I mean, my teacher used to call it like the Hong Kong problem, but it's combinatorics. So if you search up stars and bars or counting, this is what it is. Great. So Melody, do you want to take this next question?
Yeah, I think I can do this next one, but this makes me wonder if this problem is like mixing difficulty or if this is actually number 11 on the test and it just gets harder. I'm kind of scared, but let's look at this next question. Okay, so this reads, what is the sum of all integers x that satisfy the inequality x squared plus 14x is less than or equal to negative 29? Oh, as someone mentioned, 29 is prime, so that makes it kind of hard to factor this nicely. So normally I'd move 29 to the other side, but I'll just leave it here just for the sake of this problem. So if I factor out an x, I can get x times x plus 14 is less than or equal to negative 29. So what this tells us is that one of these has to be negative and one of them has to be positive, or else it won't be negative. Because negative 29 is negative, and anything less than that is still negative. And obviously, if we add 14 to a number, it's not going to get smaller. So we know that x has to be negative and x plus 14 has to be positive. Yeah, you're exactly right. I see someone put that in the chat. Yes, x is always less than x plus 14. So we know that x is less than 0 and x plus 14 is greater than 0. So let's test a few numbers. If we want x to be less than 0 and x plus 14 to be greater than 0, let's try x equals negative 1. Then x plus 14 is 13, but then negative 1 times 13 is negative 13, which isn't less than 29, or negative 29. So if we keep going, we don't have to go that far. We see that if x equals negative 3, then x plus 14 equals 11. And negative 3 times 11 equals negative 33. So this is the first number we get that's less than negative 29. So now, oh, I did not mean to show the answer. I'm so sorry. I need to make a new slide. So we have x equals negative 3 and x plus 14 equals 11 as our first pair of numbers. And x equals negative 4 works because then we get 10 and this is negative 40. So let's just write a couple of dots to show that we know it'll keep going. And these numbers kind of form pairs, like as x goes down by 1, x plus 14 also goes down by 1, but it'll eventually like collide because these are negatives and these are positives. So when it goes to negative 5, this will go to 9. It's kind of sort of symmetrical with an odd center. So that means that if we want to go to another negative 33, we need to find out what makes x plus 14 equals 3 and x equals negative 11, I think. So this also makes negative 33, which is less than negative 29. And we can try x equals negative 12 just to verify. If x equals negative 12, x plus 14 equals 2. Negative 12 times 2 is negative 24, which is not less than negative 29. So let's just get rid of this. We don't care about this. Let's go back to the problem. What did it actually ask us? What's the sum of all integers x that satisfy this inequality? Yeah, so x is an integer. Technically, x could be anything between negative 3 and negative 11, but this problem only wants integers, which is perfect. So now we have -3, -4, a lot of other stuff, and then -11. These are all of our values of x that work, or integer values of x that work. So now we just need to add it all up. So let's go ahead and ignore the negatives because -3 plus -4 plus -11, oops, not -111, -11 equals -3 plus 4 plus, and usually we make less mistakes when working with positive numbers. So let's just only look at like this part for now. So I think we know how to add this, yeah, with grouping. So this is such a cool way to do things. I'm a big fan of this strategy. Let's add a 10 here, just so we can see what we mean by grouping. So we can like put the 3 and 11 together and the 4 and the 10 together, and it'll keep going. So 3 plus 11 is 14, 4 plus 10 is 14. If you keep going in, 5 plus 9 is 14, and so on. So we have how many groups of 14? Can anyone put that in the chat? Yes, there are 7 pairs. Oh, 7 pairs? Oh. Oh, pairs have 2 numbers. Oh, okay. So this is kind of tricky because there is an odd number. Sorry, I forgot to mention that. So if you go in far enough, there's an odd number of them. So a cool way to do this is just think of it as averages. So we can just count the numbers between 3 and 11. 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 9 numbers. And their average is the average of the ones on the end. Since they add to 14, their average is 7. So the average of all the numbers is 7, and there's 9 numbers, so that's 63. But is our answer 63? Because don't forget, we have a negative over here. You can take it out, but you can't forget about it at the end. So yes, the answer should be -63. And yeah, I'm seeing a lot of people talking about the pairs again. Just remember that if there's one left over, don't freak out. It still works the same way. So it should be -63. Yes, the sum of the values for integers x is -63.
Great, great, great. So now let's take a look at the next question. Okay. I already foresee that there's gonna be a little bit of a bonus extension thing after we're done solving the question. But let's just solve the question first. Okay, so the question says that given 5x plus 5y equals 57 minus 6xy and x equals 3xy minus 18 minus y, what is x squared plus y squared? So pretty standard stuff. 2 equations, 2 variables. 5x plus 5y equals 57 minus 6xy, and we have x equals, ooh, that was big X, 3xy, well, 3xy, y minus, well, what the heck, what, minus 18 minus y. Okay, and then we're asked for x squared plus y squared. So if we solve what x and y is, that would be a lot harder than this question needs to be. There's actually a very simple trick that makes this question a lot easier because the question, so first, the question is not asking us about x and y's. So if we think about it mathematically, do we really need to know x and y? There's actually a way to solve this without finding out what x and y is. And that is by finding out instead by using x plus y and by using x times y. So let's call x plus y a, and let's call x times y b. X, y is a, x plus y is a, and x times y is b. So if we substitute this, let me just change the second equation. So the second equation, you see this right here, I'm going to take this y, and I'm going to move it to the other side. So I have x plus y equals 3xy minus 18. Great. So now let's look at equation 1 right here. And equation 2, I'll take it right here. So equation 1, we can write that, whoopsies. We can write that as, oh, there we go. 1 equals, well, 5x times y is, let's move down here, 5a, right? Equals 57 minus 6x times y is 6b. Now let's look at the second one. Okay. X plus y is a. 3xy is 3b minus 18. So guys, look at, well, guys and girls, everybody listening, look at this. Look at this equation. Isn't this beautiful? Look how simple this equation is. Oh my gosh. So let's solve it. Let's solve it. Let's say a equals 3b minus 18. Let's substitute it into the first equation. Substitution, you guys know the drill. 5, 3b minus 18 equals 57 minus 6b. Oh, whoopsies. What the? Okay, there we go. Now let's expand 15b minus, this is 90. I'm sure you guys can know how to do this. Equals 57 minus 6b. Okay, let's move this 6b. Oh, let's move this 6b over to this side. We get 21b. Let's move this 90 over to that side. We get 147. So b equals 7. Okay, b equals 7. Cool. What does a equal? Okay, let's substitute this. B equals 7 back in this equation right here. A equals 3b minus 18. So A equals 3 times 7 minus 18. A equals 21 minus 18. A equals 3. Wow, guys, this algebra was very easy, but there's one more trick that brings it all together. Because, guys, the question is asking us about x squared plus y squared. If I give you a and b, well, what are you supposed to do with a and b? But guys, look, a equals x plus y equals 3. B equals x times y equals 7. So what happens? How do I connect xy and x plus y together with x squared plus y squared? Well, squares make us think of squares, right? Like they're squares. So the trick is to square question A. Oh, this is not working. There we go. Wait, my mouse. There we go. X plus y squared equals 9, right? Because I just squared both sides of this equation. So that means that I get, my mouse is broken again. Okay, x squared plus 2xy plus y squared equals 9. But guys, look at this. This orange stuff is the stuff that I want. And this yellow stuff is this is the stuff that I don't want. But what do I know what 2xy is. 2xy is 2 times b, which is 14. So I get x squared plus 14 plus y squared equals 9. So that means that x squared, whoops, there we go. X squared plus y squared equals -5. And if we look at the answer key, bam, it's -5. Look at that, black magic. Because we didn't actually solve what x and y is, but we solved what x squared plus y squared is. Is that the quadratic formula? No. But it's the substitution. It's the sum and product substitution. Sometimes when we're asked for symmetric expressions that are not related, that do not ask us exactly for x and y, we don't solve for x and y. We solve for x plus y and x times y. Great. Now, Melanie, do you want to take us through the next one?
Yes, the next one is a pretty interesting problem. So it says that quadrilateral ABCD, oh, I'll make mine bigger, actually. Quadrilateral ABCD is inscribed in a circle. And given that ABC is an isosceles right triangle with right angle BAC, how many degrees is the sum of the measures of angle CAD and ACD? I think we should first draw the triangle before drawing the quadrilateral. I think it'll make this problem easier. So let's draw a circle. It's much easier to draw stuff inside circles than circles around stuff. So given that ABCD is an isosceles right triangle with right angle BAC, an interesting thing to know about right angles in circles is that a right angle, if like you have one on the side of a circle, it'll always, oh, it's so hard to draw. I'll draw this first. It's always from a diameter. So like, if you know this is a right angle, wherever the lines end, this is always going to be a diameter of the circle. Very important to remember. I know it doesn't look like it, but that's just because I'm very bad at drawing circles. So the right angle is BAC. So make sure to read which one's the right angle. So let's say this is B, this is A, and this is C. Oh, but it's quadrilateral ABCD inscribed in a circle. So don't be tripped up by this. I almost did. So if it's ABCD is inscribed in a circle, that's A, B, C. D has to be somewhere over here. It's not over here. I might look at it, look like it, but D is actually somewhere between A and C. So let's just say it's over here. Let's start a new slide so it's not as squished. Well, the circle's even worse. I don't think there's like a circle option on here, so we're just gonna have to deal with my bad circles. So we know that ABC is an isosceles right triangle too. So these two side lengths are the same. Just so we have more room. Was it? I forgot which angle is the right angle. BAC is the right angle. Okay. BAC and D, let's just call this D. Oh, the question, I'll go back to it for a little bit. So we just have a quadrilateral inscribed in a circle, and it wants us to find the sum of the angles. I'll go back to the questions once I draw the angles, because they're not actually there yet. And I'm sorry, there's no prize for having the most stars. It's just bragging rights. You can go back to school and tell all your friends that you got a ton of stars. So this is our actual quadrilateral. Oh, I just realized you can't see my point D. This is point D. Okay, so our quadrilateral is A, B, C, D. And what did the question ask us to find? The sum of CAD and ACD. Okay, so CAD is this one, and ACD is this one. So we want to find the sum of these. Let's just label everything we have for now. We know that this is a right angle, and since it's isosceles, this is 45, and this is 45. That's interesting. So there's also a really cool theorem, I think, that says a cyclic quadrilateral, the opposite angles add up to 180. So a cyclic quadrilateral is just any quadrilateral you can put a circle over. So this is definitely a cyclic quadrilateral. It told us in the in the question. What if it was a square? I don't think it could be a square because then D and C would have to be on the same point because we know that BAC is the right angle. And if you have like D in between A and C, it can't be a square unless D was on C. So if we use that super cool thing about the opposite angles, we know that D plus B, like this angle D and the angle of B, has to add up to 180 degrees. So ADC plus 45 equals 180 degrees. That gives us ADC equals 135 degrees. And This might seem completely unrelated, but oh, the opposite angles are DB. Yes, D and B, these are the angles opposite to each other, and A and C are the angles opposite to each other. So this helps us because the sum of BAC and ACD is actually, well, we can notice because it's in a triangle. So those two angles plus the angle D is 180 degrees because the degrees in a triangle are 180 degrees. So we can write that out too. So ADC plus the thing that we want, let's just call that X, equals 180. So do we see how that connects here? ADC is 135, and that plus the thing we want is 180. So 135 plus the thing we want is 180. So the thing we want is 45 degrees. Why is ADC plus 45 180 again? ADC. Oh, because there's this really cool theorem that says like the angles opposite of each other in a quadrilateral that can be circumscribed by a circle equals 180. It's just a cool thing to remember. I'm sure there's a way to prove it, but it's just a good thing to have in your pocket for contests because you don't have time to prove everything on there. What about angle CAD? We actually don't need to find them separately because we know that them added together plus the whole angle D is 180 because there's 180 degrees in a triangle. Just like in the last question, when math contest writers have you like find separate things added together, they're trying to do you a favor. So you don't actually have to find them separately. Imagine how hard the last problem would have been if you actually tried to find X and Y. Oh, there's a proof for the theorem. Thanks, Thomas. And I think we ended up with 45. Let's check that. Yes, 45. Sorry, it's so small. Okay. Sorry, I went over time.
Yeah. So, okay. We went 2 minutes over time, which honestly I think is like amazing. So we're pretty much on time, and you guys are now free to leave. But just taking a poll, the next question is actually really cool. So do you guys want to stay? If all of you guys are free to leave, but if you guys want, are you guys interested in staying to hear the solution to the next question or no? I think the next question might be, okay, well, you guys were free to leave earlier too, but stay, sure. I think this question might be the most interesting, the most mathematical, and the hardest question that I've seen today out of all the questions we've done. Great. So you guys want to say, I'll try and keep it fast, okay? So this is for the people who thought like the questions earlier were easy. So, and I'll give you guys a minute to think in the middle too. So how many 4-digit positive integers have the property that each digit is at least 2 less than the digits to its left? So what we have is we can have like 3, 5, 7, and 9. Because look, 3 is at least 2 less than 5. 5 is less than 7. 5 is 2 less than 7, and 7 is 2 less than 9. So what we can have is these numbers like that. But for example, what we can't have, we can have 2, 5, 7, 9. That also works. But we can't have 3, 6, 7, and 9. Because look, 6 and 7 are only 1 apart. So how units digit needs to be 6 or more? Yes, that is true. But then if we have 6 or more, we have 6, 7, 8, 9. And if you end up doing like stuff like this, you'll end up splitting cases. And in every case, it's very hard to figure it out. So you'll end up having to count. So for this question, the answer is not that big. It's like 30-ish. But if this question had a larger answer, what if it was 5 digits? Then, well, actually, what if the numbers were a little bigger, or it was base 12, or something like that? You wouldn't be able to count it. So there's actually a really, really, really cool trick to this. It's a little flavorful though, so I feel like it's like up to interpretation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, nine balls. Okay, so 9 balls, and then let's say I'm just gonna draw this. So I call this diagram 3, 5, 7, 9 because there's 3 balls before the first bar, so that's a 3. There's 5 balls before the second bar, so that's a 5. There's 7 balls before the third bar, so that's a 7. And there's 9 balls before the last bar, so that's a 9. So I call this 3, 5, 7, 9. And notice that there's 2 balls in between the 2 bars because there has to be at least 2 in between, right? Yeah, I turned the problem into combinatorics. But the trick is, I call it I don't have a name for this, but let's call it the kidnapping method. So first, I can't have, if I have ball, 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 bar, ball, bar, ball, 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 bar, that doesn't work because there's only 1 ball in between here, but there has to have at least 2 balls, right? There has to have at least 2 balls. There could be 3 balls, there could be 4, but there has to be at least 2. So what I'm gonna do is I'm gonna take glue, I'm gonna take super glue, and I'm gonna take these 3 balls, these 2 balls, okay. I'm gonna take these 2 balls and I'm gonna super glue it to that bar. I'm gonna take these 2 balls and super glue it to that bar. I'll take these 2 balls and super glue it to that bar. And this one doesn't matter, right? Because I can start with 1. I can start with 1. I can't start with 0, but I can start with 1, right? So what ends up happening is, wait 1 second, let me check my work. Okay. 8:06. Okay, we have more time. So what ends up happening is, let's just wait, wait a second. 1, 2, 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1 second, guys. Yeah, okay. We'll figure it out later. So what happens is I'm gonna call this a digit, right? This is a digit, but this box is also a digit. Let me change colors actually. This box is also a digit. This box is a digit. And this box is a digit. So what I end up with is these 4 boxes, box, 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 box. And I have these extra balls in the front. So what I can do is, wait. This is a little sus. I think the answer is, okay, I'll show you the solution that gives the right answer, but I think the solution is wrong. I don't know what's going on. But so we have 3 balls and we have 4 boxes. So what I can do is I can take these balls in the front. They can be anywhere. They could be in here, they could be in there. So what I have is 7 total objects, and I'll have 7 choose 3. And that's going to give me 7 times 6 times 5 divided by 3 times 2, which is 35. And that's what the answer is. So the answer is 35. But I think the answer is the answer wrong? I don't know what's going on. Yeah, but okay, so this is sticks and stones. So the issue is it's a 4-digit number, right? Positive integers is at least 2 less than digits to its left. The problem is that in this, when we're writing this, the first ball has to stick to the first bar too, because you can't have no balls. Like you can't take all 3 of these balls and move them out, or else the first bar is gonna be a 0. But anyways, this is the key idea, and we're getting a little over time. But this is idea of where you take sticks and stones, you represent it combinatorically, and then you super glue the balls to the bars, and then you end up with these boxes, these arbitrary mathematical boxes, and you have these spare balls left over here, and you can just put them everywhere and use sticks and stones or stars and bars, and you end up with 7 choose 3, which is 35. And that gives us the right answer. Good job, guys. All right, thank you. Any questions? Wait, I can stay for questions too, but the rest of you guys are really, really super free to leave. But if you guys have any questions, I can stay. Bye bye, bye bye. Thank you, thank you. Bye, guys. Bye
Thank you for
bye.
staying over.
Yeah, thank you,
That
thank
was
you. Bye,
actually such a cool
Tessin.
question. I'm glad
No
I
problem,
stayed.
Simon. Bye, Kathy. AT caught up nice.
Bye.
Bye, Valerie. Bye, Ed.